Picture this: a single explosion so powerful it outshines an entire galaxy, blasting stardust across the cosmos for millions of years. This isn't science fiction. It's a supernova, one of the universe's raw displays of power. Forces like these sculpt galaxies, bend time, and dictate the fate of everything we know. Yet they're invisible, silent, operating on scales so vast they defy human intuition. Today, we're pulling back the curtain on the 30 most powerful forces in the universe, from the crushing grip of black holes to the mysterious push of dark energy phenomena, so immense they make even the mightiest earthly powers seem insignificant. Think of gravity as the quiet architect of the cosmos, tirelessly shaping planets and stars over eons, while dark energy works in the shadows, stretching space itself like an infinite rubber sheet. These forces don't just exist out there, they're part of you right now. The iron in your blood, forged in the heart of a dying star, the warmth of sunlight. A tiny ripple from a nuclear furnace 93 million miles away. The universe isn't some distant stage. It's alive in every atom, every heartbeat, every moment. So what makes one force stronger than another? Why do some rule entire galaxies while others flicker out unnoticed? The answers lie in extremes: temperatures hotter than a billion suns, pressures that crush matter into diamonds the size of planets, energies so vast they rewrite the laws of physics. Over the next 30 revelations, we'll journey from the familiar tug of gravity to the eerie frontier of quantum entanglement, where particles communicate instantly across light years. By the end, you won't just understand these forces, you'll feel them, as if the cosmos itself is whispering its secrets directly to you, ready to begin. Gravity is the silent hand that holds the universe together, the unseen sculptor molding galaxies and planets from the cosmic dust. It's the reason stars ignite, planets orbit, and black holes devour everything that strays too close. Newton called it a force pulling apples from trees, but Einstein revealed its true nature: gravity isn't just a tug. It's the bending of spacetime itself, a cosmic trampoline where every object warps the fabric around it. Picture a bowling ball placed on a stretched sheet, causing marbles to spiral inward. That's gravity shaping reality on the grandest scale. Yet for all its cosmic dominance, gravity is surprisingly feeble. A fridge magnet can defy Earth's entire pull on a paperclip, and a single spark of static electricity overwhelms gravity's grip. So why does it rule the universe? Because it never turns off. While other forces cancel out or fade with distance, gravity adds up over vast reaches, drawing galaxies into clusters and weaving the largest structures in existence. Without it, stars would never have ignited, planets would never have formed, and life as we know it would be impossible. Even black holes, gravity's most extreme expression, bend the rules we thought were unbreakable. They twist space-time so violently that not even light escapes, creating cosmic whirlpools where time itself slows to a crawl. And yet, for all their destructive power, black holes are also creators. Their gravitational dances fling stars across galaxies, seeding new solar systems with the elements for life. Gravity is the universe's paradox: weak enough to let you jump, yet strong enough to shape eternity. If gravity is the universe's architect, electromagnetism is its artist, painting the cosmos with light, binding atoms into molecules, and weaving the invisible threads that power everything from stars to smartphones. While gravity whispers its influence across vast distances, electromagnetism shouts with fireworks of energy, governing the chemical reactions that build planets and the auroras that dance above them. It's the reason your hand doesn't pass through solid objects, the force behind every spark, every glow, every signal racing through the air. James Clerk Maxwell unlocked its secrets in the 1860s with 4 elegant equations, revealing that electricity and magnetism aren't separate forces but two sides of the same cosmic coin. Picture a river of charged particles flowing through space. This electric current creates a magnetic field, which in turn generates more electricity, a self-perpetuating dance that radiates outward as light. Together, these waves form the electromagnetic spectrum, from radio waves longer than skyscrapers to gamma rays smaller than atoms, each carrying energy across the universe at the speed of light. What makes electromagnetism staggeringly powerful is its versatility. It's the glue holding electrons in orbit around atomic nuclei, ensuring matter doesn't simply dissolve into chaos. At the same time, it's the engine of stars where crushing gravity fuses hydrogen atoms, releasing electromagnetic energy as sunlight, a process that's warmed Earth for 4.5 billion years. And then there are the auroras, those celestial curtains of color, born when solar winds slam into our atmosphere, exciting atoms to release photons in a shimmering display of electromagnetism's raw beauty. Yet unlike gravity, which only attracts, electromagnetism plays both sides, repelling and attracting with equal ferocity. A magnet's poles push apart with enough force to levitate trains, while static cling defies gravity's pull on a balloon. This push and pull dynamic gives electromagnetism infinite range in theory, though its effects weaken over distance as positive and negative charges cancel each other out. That's why we don't feel the tug of distant stars' magnetic fields, even as their light reaches us across millennia. Electromagnetism is the universe's great paradox, delicate enough to power a firefly's glow, yet fierce enough to shape the destiny of galaxies. Deep within every atom, an invisible titan wages a silent war, the strong nuclear force, the mightiest glue in the universe. While electromagnetism makes protons repel each other with fierce intensity, this force locks them together in atomic nuclei with a grip 100 times stronger than electricity's push. Without it, matter itself would fly apart in a flash of repelling charges, leaving no stars, no planets, no chemistry, just a thin soup of lonely particles drifting through darkness. The secret lies in quarks, the universe's smallest building blocks. Protons and neutrons aren't solid beads but bustling cities of 3 quarks each, bound by sticky particles called gluons. These gluons act like cosmic rubber bands, stretching between quarks but never snapping. Pull 2 quarks apart, and the energy stored in that stretch creates new quarks before they can separate, nature's ultimate lockdown. This quark glue doesn't just hold particles together, it leaks out slightly, creating a residual force that binds entire nuclei. That's why cramming protons into a tiny space, like the heart of a star or a particle collider, overcomes their electromagnetic hatred with nuclear teamwork. Stars are the ultimate strong nuclear force laboratories. In their cores, gravity smashes hydrogen nuclei together so violently that the strong force takes over, fusing them into helium and unleashing sunlight. This same process, scaled up in supernova, forges elements like gold and uranium, meaning the ring on your finger owes its existence to this force's unbreakable grip. Yet despite its power, the strong force has shockingly short range. Step just 1 femtometer, a millionth of a nanometer outside a nucleus, and it vanishes completely, like a whisper drowned by electromagnetism's roar. Particle accelerators reveal its true might. When scientists slam protons together at near light speeds, the energy briefly unravels the strong force's work, freeing quarks in a primordial plasma hotter than the early universe. For a split second, matter reverts to its rawest form, a flashback to the first microseconds after the Big Bang. Even there, the strong force never truly lets go. It just reshapes itself, proving it's not just a force but the universe's ultimate sculptor of matter. While the strong nuclear force builds atomic nuclei like an unshakable fortress, the weak nuclear force plays the cosmic saboteur, subtly rewriting matter from within. This shadowy operator works on an unimaginably tiny scale, 1,000,000 times shorter than the strong force's reach, yet its effects ripple across the universe. It's the reason stars shine, the force behind radioactive decay, and the invisible hand that transforms neutrons into protons, rewriting the blueprints of atoms themselves. Take the Sun's furnace, for example. Deep in its core, hydrogen fuses into helium not just through the strong force's brute strength, but via the weak force's delicate interventions. When two protons collide, one must flip into a neutron for fusion to continue, a trick the weak force alone can perform. This metamorphosis spits out a neutrino, a ghostly particle that streaks through space almost unnoticed, carrying away energy that eventually becomes sunlight. Without this quiet alchemy, stars would fizzle out before igniting, leaving the cosmos dark and lifeless. Radioactivity reveals the weak force's transformative power in action. When unstable elements like uranium decay, the weak force nudges neutrons into protons or vice versa, transmuting elements over millennia. A chunk of uranium slowly becomes thorium, then radium, then lead nature's own slow-motion wizardry. This process heats Earth's core, drives geothermal vents, and even powers our nuclear reactors, where split atoms release energy originally stored by the weak force's ancient handiwork. Particle accelerators expose its strangest quirk. The weak force is the only one that changes particle identities. When scientists smash atoms, they catch glimpses of W and Z bosons, massive, short-lived carriers of the weak force that vanish in a trillionth of a second. These phantoms are so heavy they make protons look feather-light, explaining why the weak force fades so quickly compared to electromagnetism's infinite reach. Yet for all its subtlety, this force leaves fingerprints everywhere. In the neutrinos streaming through your body right now, in the radioactive isotopes dating ancient fossils, even in the carbon atoms that form the backbone of your DNA. What makes the weak force uniquely eerie is its partnership with neutrinos, particles so elusive they pass through light years of lead without a single collision. Every second, trillions of solar neutrinos zip through you unnoticed, remnants of weak force interactions in the Sun 8 minutes ago. Detectors buried deep underground occasionally catch these phantoms, proving the weak force's reach extends far beyond its microscopic playground. It's a paradox of scale, a force too feeble to hold atoms together, yet powerful enough to reshape the elements that build worlds. The cosmos holds its greatest secrets not in the blazing light of stars, but in the invisible threads weaving through the void. Dark matter and dark energy, two phantoms accounting for 95% of the universe's total content, dictate the fate of galaxies and the rhythm of cosmic expansion, yet remain utterly unseen. Imagine walking through a pitch-black room, feeling gusts of wind tug at you from all sides, objects moving as if pushed by invisible hands. That's the universe we actually live in. Dark matter's presence betrays itself through gravity's ghostly fingerprints. Spiral galaxies like the Milky Way rotate so fast their outer stars should fling into the abyss, yet something holds them in place. An enormous halo of dark matter, its gravitational embrace far outstripping the pull of visible stars. Picture a merry-go-round spinning wildly, its steel frame groaning, but the children clinging to the edges don't fly off because unseen ropes anchor them. That's dark matter's handiwork, an invisible scaffold binding galaxies together. Simulations of the cosmic web reveal its staggering scale, colossal filaments of dark matter stretching billions of light years, guiding galaxies into glittering clusters like beads on a string. Without it, the universe would lack the structure for life as we know it. Then there's dark energy, the universe's most baffling repulsive force. In the late 1990s, astronomers made a chilling discovery. Not only is the cosmos expanding, but that expansion is accelerating, as if space itself is being stretched apart by some anti-gravity. Redshift observations of distant supernovas showed galaxies fleeing faster over time, their light stretched into crimson whispers. Think of blowing up a balloon with tiny dots on its surface. As it inflates, dots move apart. But if the balloon suddenly started expanding faster on its own, you'd know something eerie was at work. That's dark energy's signature, a relentless push against gravity's pull, dominating the universe's energy budget and steering it toward an ever colder, emptier future. What makes these forces so unsettling is their asymmetry. Dark matter clumps sculpting the universe's architecture through gravity, while dark energy permeates space uniformly, its density constant even as the cosmos grows. One builds, the other erodes. Together, they're locked in a cosmic tug-of-war, with dark energy currently winning galactic clusters, will one day drift apart so completely that no future civilization will see anything beyond their own starless horizon. Yet without dark matter's gravity, galaxies might never have formed at all, and without dark energy's push, the universe could have collapsed back on itself eons ago. These hidden forces don't just shape the cosmos, they wrote the rules for existence itself. At the heart of nearly every galaxy, a monster lurks, an unfathomably dense beast with gravity so fierce it bends light into submission. Supermassive black holes are the universe's ultimate power brokers, weighing in at millions to billions of times the mass of our Sun. Their event horizons, the points of no return, stretch wider than our entire solar system, swallowing gas, stars, even other black holes with terrifying indifference. But these cosmic giants aren't just destroyers, they're creators, shaping the very galaxies that host them. Take the first ever image of a black hole, captured in 2019 at the core of galaxy M87. That fiery ring isn't the monster itself. It's the glow of superheated plasma spiraling into oblivion at nearly light speed, warped into a halo by gravity's grip. The darkness at its center, a shadow cast by the event horizon, a boundary where space-time folds so steeply that not even photons can climb out. This 3 million-degree maelstrom pumps out energy equivalent to 1 trillion suns, powering jets of matter that blast across 55,000 light-years, 5 times the Milky Way's width. What's chilling is how calmly these titans feed. When a star drifts too close, tidal forces stretch it like taffy in a process called spaghettification. Gas from the shredded star forms a swirling accretion disk, heating up to X-ray temperatures as it inches toward the abyss. Some of this matter doesn't fall in. It gets catapulted out in relativistic jets, narrow beams of particles moving at 99.9% light speed. These jets can outshine their entire host galaxies, visible across the universe as quasars, nature's most powerful lighthouses. Yet black holes might also be galactic architects. The Milky Way's silent heavyweight, Sagittarius, a star, sits quietly now, but its mass tightly choreographs the orbits of billions of stars around it. Computer simulations suggest that without such central anchors, spiral galaxies would lose their elegant shapes, their stars scattering into chaos. Even more intriguing, the brightness of quasars in the early universe hints that black holes may have helped ignite star formation by compressing gas clouds with their gravity, jump-starting stellar nurseries. Here's the paradox: the same force that tears stars apart might have paved the way for new ones. When two galaxies collide, their central black holes eventually merge, releasing gravitational waves that ripple through space-time. These cosmic mergers could fling stars into new orbits, seeding fresh stellar generations. It's a reminder that in the universe's grand balance sheet, destruction and creation are two sides of the same coin, and supermassive black holes hold the ledger. Two dead stars spiral toward each other in a final, fatal dance. One wrong move, and the universe will never be the same. When neutron stars collide, they don't just explode, they detonate with the force of 1 billion suns, ripping spacetime apart and scattering the rarest elements in existence. This is a kilonova, nature's ultimate alchemy lab, where gold, platinum, and uranium are forged in the crucible of extreme physics. Picture two city-sized objects, each heavier than our Sun, spinning hundreds of times per second as they draw closer. Their immense gravity warps space so severely that if you stood on one, the other would appear larger than the full moon, even 100 miles away. When they finally touch, the impact converts an entire Earth's mass worth of material into pure energy within milliseconds, a shockwave that briefly outshines every star in the Milky Way combined. But the real magic happens in the debris, the extreme conditions, 1 trillion degrees, pressures rivaling atomic nuclei force neutrons into atomic cores at unbelievable rates. This rapid neutron capture, or R process, transforms simple atoms into heavy elements like gold and platinum. A single merger can produce hundreds of Earth masses worth of these precious metals, flinging them into space at near light speed. That wedding ring on your finger, its atoms likely began their journey in a cataclysm like this, launched across the cosmos before our solar system even existed. In 2017, humanity got front-row seats to this spectacle, when LIGO detected gravitational waves from neutron star collision GW170817. Telescopes worldwide swiveled to catch the aftermath. The data confirmed theories, gamma rays, X-rays, and a glowing cloud rich with heavy elements. But the most haunting evidence came from LIGO itself, the sound of spacetime vibrating like a struck bell as the stars merged. Converted to audio, it's a soft chirp that rises in pitch before abruptly cutting off the literal sound of two neutron stars becoming one. What makes these events so pivotal isn't just their destructive power, but their creative potential. The gold in your electronics, the platinum in medical devices, even the uranium fueling reactors, all were likely born in such explosions. Kilonovas are cosmic recycling plants, turning the ashes of dead stars into the building blocks of new worlds. And with each merger we detect, we're glimpsing the violent origins of the very atoms that make up our bodies, our planet, and everything we've ever known. In the blackness of space, a sudden flash erupts brighter than 1,000,000 trillion suns, packing more energy than our star will emit in its entire lifetime. Gamma-ray bursts are the universe's most violent outbursts, cosmic screams lasting from milliseconds to minutes, yet capable of frying planets halfway across the observable universe. Born from the deaths of hypermassive stars or the mergers of neutron stars, these events are so intense they momentarily outshine every star, galaxy, and quasar combined. Hypernova, the engines behind long gamma-ray bursts, are stellar deaths that make supernova look like firecrackers. When a rapidly spinning star 30 times heavier than our Sun collapses, its core doesn't just implode, it forms a black hole while twin jets of plasma, accelerated to 99.99% light speed, drill through the dying star. These jets, focused tighter than a laser beam, become gamma-ray bursts, carrying enough power in seconds to rival the output of entire galaxies. Any planet within their narrow beam faces instant sterilization, ozone layers vaporized, atmospheres scorched, and surface life bathed in lethal radiation. The Fermi Gamma-Ray Space Telescope has captured these death rays in action. In 2008, it detected GRB 080319b, a burst so bright it was briefly visible to the naked eye despite erupting 7.5 billion light-years away halfway across the observable universe. Its afterglow lingered for weeks, revealing heavy elements like platinum and gold forged in the explosion. Another burst, GRB 130427a, unleashed in 5 seconds what our Sun would take 5 billion years to emit, its photons so energetic they couldn't all be measured by Fermi's instruments. What makes gamma-ray bursts truly unsettling is their unpredictability. Unlike supernova, which give days of warning as their stars brighten, these bursts arrive without preamble, flashes of annihilation from random corners of the cosmos. One theory suggests a nearby burst 450 million years ago may have triggered Earth's Ordovician mass extinction, stripping the atmosphere's protective layers and unleashing a cascade of environmental collapse. Today, astronomers scan the skies not just out of curiosity, but as an early warning system for these celestial death rays. Yet there's a strange beauty in their violence. The afterglows of gamma-ray bursts serve as cosmic lighthouses, their light piercing through intergalactic dust to reveal the universe's structure. By studying their spectra, scientists have measured the composition of galaxies billions of light-years distant, uncovering the distribution of matter in the cosmos' youth. These bursts don't just destroy, they illuminate, etching their signatures across space-time as reminders of the universe's raw, untamed power. Imagine the entire observable universe, every galaxy, every star, every atom, compressed into a space smaller than a single proton. Now picture that infinitesimal speck exploding outward, doubling in size every trillionth of a trillionth of a trillionth of a second until it surpasses the scale of our cosmic horizon. This wasn't just any expansion, it was cosmic inflation, the universe's most explosive growth spurt, stretching space-time itself faster than light could chase it. The evidence for this staggering event is etched into the oldest light we can see, the cosmic microwave background. Those faint temperature variations mapped by satellites like Planck aren't random noise. They're quantum fluctuations from the universe's first moments, stretched to cosmic proportions by inflation's relentless pull. Picture a ball of dough with tiny raisins scattered throughout. As the dough expands exponentially, the raisins drift apart, their original microscopic imperfections now defining vast voids and galaxy clusters. That's how quantum jitters became the seeds of everything, each ripple in the cosmic microwave background a blueprint for future superclusters. What fueled this hyper-expansion? Theorists point to the inflation field, a mysterious energy state that temporarily rewrote the rules of physics. Like a snowball rolling downhill, this field's energy drove exponential growth until it abruptly decayed, converting its pent-up power into the primordial particle soup of the Big Bang. But here's the twist: some regions of space might have escaped this decay. If inflation didn't stop everywhere simultaneously, pockets of the universe could still be ballooning endlessly right now, spawning separate bubble universes with entirely different laws of nature. The implications are dizzying. Our observable cosmos may be just one island in an infinite multiverse, each with its own unique physics, some sterile, some brimming with life, most utterly alien. And if colliding bubble universes leave scars in the cosmic microwave background, as some models suggest, we might one day find proof we're not alone in the inflationary sea. Until then, inflation remains the ultimate origin story, a force so potent it turned quantum whispers into galactic thunder, setting the stage for every atom, every star, and every curious mind that ever wondered how it all began. Among all cosmic doomsday scenarios, none unsettle physicists quite like vacuum decay, the possibility that our universe isn't in its most stable state, but teetering on the edge of annihilation. The Higgs field, which gives particles their mass, might currently exist in a false vacuum, a precarious valley in the cosmic energy landscape. If a quantum fluctuation nudges it into a deeper, truer valley, the consequences would rewrite reality itself. Picture a snowfield primed for an avalanche. One stray vibration could trigger a wave of transformation racing outward at light speed, erasing the fundamental laws we rely on. This isn't science fiction, it stems from the very equations describing particle physics. In the Standard Model, the Higgs field's energy state determines the masses of electrons, quarks, and even the atoms they form. Right now, it's like a marble resting in a shallow depression on a hillside. But if the field tunnels through its quantum barrier into a lower energy state, the marble would roll catastrophically downhill, and the slope of that new valley could reconfigure particle properties instantly. A bubble of true vacuum would expand relentlessly, its boundary altering the forces of nature as it passes. Stars, planets, and life itself would dissolve into new forms of matter obeying alien physics before anyone could blink. The visual is both chilling and mesmerizing. Astrophysicists simulate this as a sphere of redefinition, a wave front where chemistry, nuclear forces, and even light's behavior change abruptly. Within the bubble, the Higgs field's new value might make electrons too heavy to form atoms or quarks too light to build protons. The shock wave wouldn't just destroy, it would transmute, rewriting existence with rules we can't predict. Theoreticians calculate such an event could already be racing toward us from a distant galaxy, undetectable until it arrived, yet there's a strange comfort in the numbers. The probability of spontaneous vacuum decay in our observable universe is astronomically low, perhaps 1 chance in 10 to the power of several hundred over billions of years. The Higgs field has likely held its current value for 13.8 billion years, suggesting remarkable stability. But the sheer scale of the cosmos means that if it's possible, it's inevitable somewhere. Somewhere in the infinite expanse beyond our horizon, bubbles of true vacuum may already be blooming, their boundaries rewriting physics in their wake. What makes vacuum decay uniquely haunting isn't just its lethality, but its democratizing indifference. Unlike asteroid impacts or supernova, it wouldn't spare the prepared or the distant. No technology could shield against it, no warning could precede it. Yet this very extremeness underscores how delicately balanced our universe is, a fleeting equilibrium where fields and forces conspire to make life possible, if only for a cosmic heartbeat. Two particles separated by galaxies dance in perfect unison, change the spin of one, and the other instantly mirrors it, as if space and time don't exist between them. This is quantum entanglement, the phenomenon Einstein famously called spooky action at a distance, a force so bizarre it challenges our deepest intuitions about reality. At its core, entanglement defies the classical rules of cause and effect, linking particles in ways that make them behave as a single entity, no matter how far apart they drift. Take Schrödinger's cat, the famous thought experiment where a feline in a box is simultaneously alive and dead until observed. Entanglement takes this paradox further. Imagine not one cat, but two, separated by light years, their fates intertwined so that opening one box instantly determines the state of the other. This isn't just theoretical. In labs worldwide, scientists have entangled photons, electrons, even entire diamonds, proving that particles can share states faster than light could communicate between them. The moment you measure one, its partner snaps into a corresponding state, whether they're a meter apart or on opposite sides of the universe. How does this work? The mathematics of quantum mechanics describes entangled particles with a single wave function, a shared description that doesn't care about distance. When particles become entangled, their properties, spin, polarization, momentum, become correlated. Measure one and the other's state is instantly revealed, not because information travels between them, but because the act of measurement collapses their shared reality into a definite outcome. It's as if the universe maintains a hidden ledger, updating entries simultaneously across infinite space. Quantum computing harnesses this eerie connection. Traditional computers process bits as zeros or ones, but quantum bits, qubits, exist in superpositions of both states, linked through entanglement. Google's 53-qubit Sycamore processor demonstrated this in 2019, solving a problem in minutes that would take classical supercomputers millennia. The secret: entangled qubits perform calculations in parallel, exploring countless possibilities at once. A network of entangled qubits isn't just a faster computer, it's a machine operating in multiple realities simultaneously. Recent breakthroughs push the boundaries further. Chinese scientists teleported quantum states between ground stations and satellites, while Dutch researchers maintained entanglement over distances exceeding 1 kilometer in real-world conditions. These experiments aren't just academic, they're paving the way for unhackable quantum networks, where information is encoded in entangled particles, making interception impossible without detection. Even more tantalizing, some theories suggest entanglement might underlie spacetime itself, weaving the fabric of the cosmos at the most fundamental level. What unsettles physicists isn't just the spookiness, but the implication that our universe isn't locally real objects don't have definite properties until measured, and those measurements can be correlated across arbitrary distances. It's as if reality is a vast, interconnected web with entanglement stitching the seams. From quantum cryptography to black hole physics, this force doesn't just challenge our understanding, it redefines what's possible, revealing a cosmos far stranger and more interconnected than we ever imagined. Magnetic monopoles might sound like science fiction single, isolated poles of magnetism drifting through space like cosmic orphans, but their existence could rewrite physics as we know it. Every magnet we've ever encountered, from fridge decorations to Earth's own core, comes with inseparable north and south poles. Cut a magnet in half, and you don't get isolated poles, you get two smaller dipoles. Yet in 1931, Paul Dirac made a staggering prediction. If even one magnetic monopole exists somewhere in the universe, it would explain why electric charge comes in neat, discrete packages. His math suggested these particles would carry a magnetic charge as fundamental as an electron's electric charge, acting like tiny cosmic knots in the fabric of spacetime itself. The hunt for monopoles isn't just academic, it's a quest for the missing piece of grand unification. The Standard Model brilliantly describes three of nature's forces, but magnetism's asymmetry has always stood out like a sore thumb. Monopoles could bridge this gap, emerging as relics from the universe's earliest moments when electromagnetism and the nuclear forces were one. Picture the cosmos a trillionth of a second after the Big Bang, a seething soup of energy where symmetry ruled. As the universe cooled, phase transitions like water freezing into ice may have created topological defects in spacetime. These knots could persist as monopoles, cosmic fossils carrying clues to physics beyond our current theories. Modern searches are as creative as they are relentless. Superconducting loops in underground labs wait for the telltale jump in current that would signal a monopole's passage. Satellite experiments scour cosmic rays for particles with the right charge-to-mass ratio. Even Antarctic ice serves as a detector. When a monopole interacts with matter, it could leave trails of ionization visible to sensors like Ice Cube. So far, no confirmed sightings, but the absence hasn't deterred theorists. Some suggest monopoles might be hiding in plain sight, bound to ordinary matter in ways that mask their true nature, or lurking in the dense cores of neutron stars where magnetic fields reach absurd extremes. The implications of discovery would ripple across science. A confirmed monopole wouldn't just complete Maxwell's equations with elegant symmetry. It might unlock the door to quantum gravity or reveal hidden dimensions. Charged particles moving past a monopole would experience a bizarre twisting effect called the Aharonov-Bohm phase, a quantum mechanical signature that could revolutionize particle accelerators. And if monopoles are heavy enough, as some theories predict, they could even explain dark matter's gravitational grip. For now, these particles remain ghosts in the equations, but their potential to unify physics keeps the hunt alive. After all, the universe has a habit of surprising us, and the next great discovery might be lurking in a cosmic ray or buried deep in Antarctic ice, waiting to rewrite the rules. Black holes aren't the eternal prisons we once thought thanks to a quantum quirk called Hawking radiation. Even these cosmic titans slowly leak energy, fading away over timescales longer than the current age of the universe. The revelation came in 1974 when Stephen Hawking performed a staggering mental feat. He merged quantum mechanics with Einstein's general relativity near a black hole's edge, uncovering a paradox. According to quantum theory, empty space isn't truly empty. It's a seething quantum foam where particle-antiparticle pairs constantly blink in and out of existence. Near an event horizon, these fleeting pairs can get ripped apart. One particle falls in while the other escapes, stealing a tiny fraction of the black hole's energy in the process. This slow bleed has mind-bending implications. Classical thermodynamics says nothing can escape a black hole's grip, but Hawking radiation proves quantum effects punch a microscopic hole in that rule. The math reveals something eerie. The smaller the black hole, the faster it evaporates. A black hole with the mass of a small asteroid would shine with the heat of a million-degree furnace, shedding energy so rapidly it would vanish in a final explosive flash. For supermassive black holes, the timeline stretches beyond comprehension, a million trillion times the current age of the universe. Simulations bring this process to life. Picture a black hole the mass of our Sun. It would take 10 to the power of 67 years to evaporate, a 1 followed by 67 zeros. Now shrink that black hole to the size of a mountain, and the clock speeds up dramatically, its final milliseconds unleashing gamma rays with the energy of 1,000 hydrogen bombs. The James Webb Space Telescope might one day spot these dying gasps from primordial black holes formed in the early cosmos. What makes Hawking radiation revolutionary isn't just the mechanics, it's the philosophical quandary. The particles escaping carry no information about what fell in, suggesting black holes could permanently erase the universe's history, violating quantum theory's core tenet that information can't be destroyed. This information paradox has fueled decades of debate, with theories ranging from hidden firewalls at the event horizon to the idea that information gets scrambled into holograms on the black hole's surface. The most tantalizing twist: Hawking radiation might connect black holes to quantum entanglement. Recent work suggests the particle pairs involved are deeply entangled, meaning a black hole's evaporation could leave behind a universe-spanning web of quantum links. It's a reminder that even the darkest objects in creation aren't cut off from the cosmos. They're woven into its quantum fabric, whispering secrets as they fade. Every second, 65 billion ghostly particles pass through every square centimeter of your body, silent, massless, and utterly indifferent to matter's existence. These are neutrinos, nature's most elusive travelers, born in the hearts of stars, the aftermath of supernova, and even the fierce particle collisions of distant quasars. Unlike light, which bounces off surfaces or gets absorbed, neutrinos slice through planets like they're not even there. A sheet of lead a light year thick would stop only half of them. Their aloofness makes them cosmic messengers, carrying secrets from the universe's most violent events without distortion or delay. Consider the Sun's core, where nuclear fusion turns hydrogen into helium. Each reaction spits out neutrinos that reach Earth just 8 minutes later, offering a real-time snapshot of solar processes, something sunlight, which takes thousands of years to escape the Sun's dense interior, could never do. In the 1960s, scientists first detected these solar neutrinos, but there was a problem. They found only a third of the predicted number. The solution: neutrinos' shape shift between three flavors: electron, muon, and tau as they travel, a quantum quirk confirmed in 2015 by the Nobel Prize-winning Supermassive and experiment. The real showstoppers, though, are cosmic neutrinos from beyond our galaxy. In 2013, the IceCube Neutrino Observatory buried deep in Antarctic ice caught two neutrinos nicknamed Bert and Ernie, each packing energies 1 million times greater than those from particle colliders. These weren't local. Their trajectories pointed back to supermassive black holes and colliding galaxies billions of light years away. Detecting them was like finding needles in a cosmic haystack. IceCube sensors wait frozen in the darkness, watching for the rare blue flash of Cherenkov radiation when a neutrino, against all odds, finally bumps into an atomic nucleus. Then there's the haunting legacy of supernova. When star Sanjalik -69202 exploded in 1987, detectors caught 20 neutrinos hours before the light arrived, proof these particles outrace even photons when a star dies. Today, networks like Supermassive and stand ready as supernova early warning systems, poised to alert astronomers the moment a neutrino surge hints at a stellar collapse in our galactic neighborhood. What makes neutrinos revolutionary isn't just their stealth, but their defiance of expectations. They've forced physicists to rethink the standard model, hinted at undiscovered particle properties, and even offer leads in the search for dark matter. Next-generation detectors like DUNE will shoot neutrinos through 800 miles of Earth to study their oscillations with unprecedented precision. These phantom particles might hold the key to why the universe favors matter over antimatter. A tiny asymmetry in neutrino behavior could explain why we exist at all. From the sun's furnace to the void between galaxies, neutrinos are the universe's whisper network, etching stories of cosmic violence into quantum fluctuations we're only beginning to decode. Every breath you take is threaded with their passage, silent witnesses to the birth and death of stars, sliding through your bones like moonlight through glass. Cosmic strings are the universe's scars, one-dimensional cracks in spacetime forged during the Big Bang's chaotic infancy, thinner than a proton but stretching across billions of light years. Picture the cosmos cooling from an unfathomable heat, its fundamental forces snapping into place like ice forming on a pond. But just as freezing water traps bubbles and cracks, the universe's rapid phase transitions left behind defects, cosmic strings, unimaginably dense threads of pure energy warping spacetime around them like a guitar string bending a sheet of paper. These relics aren't just theoretical, they could be lurking invisibly around us. Their gravity so intense a single strand the length of our solar system might outweigh the sun. What makes strings so mesmerizing is their gravitational fingerprint. Unlike black holes which warp spacetime into pits, strings crease it like a razor's edge. Light passing near one wouldn't curve smoothly but split into twin images, a gravitational lensing effect so sharp it could create duplicate quasars in the sky. Time itself would distort near a string. Two clocks placed on either side would tick out of sync, not because one moved faster, but because the string's tension literally stretches the fabric of time between them. Imagine two spaceships orbiting a cosmic string. Sensors would show each crew aging at different rates, a real-world time machine powered by pure geometry. String theory, the ambitious framework aiming to unify all physics, gives these objects a tantalizing twist. In some models, cosmic strings aren't just effects but vibrating strands of extra-dimensional energy, their oscillations encoding the fundamental particles of nature. If colliding, they might create closed loops that evaporate in bursts of gravitational waves, or even spawn new universes in their wakes. The LIGO Observatory could one day catch these tremors, listening for the faint chirp of a string snapping in the dark. Yet for all their might, cosmic strings would be eerily hard to spot. A string passing through Earth wouldn't tear the planet apart. It would slice through like a wire through mist, leaving only a wake of rearranged starlight and faint gravitational ripples. Astronomers hunt for their signatures in the cosmic microwave background, searching for telltale temperature spikes or strange distortions in galaxy clusters. Some theories even suggest dark matter's mysterious clumping could be threaded by ancient strings, their gravity stitching the cosmos together in ways we're only beginning to fathom. The wildest possibility, strings might be time capsules from the universe's first trillionth of a second. Their structure, density, and distribution could reveal what happened when all forces were one, before gravity split from the quantum realm. Finding one would be like discovering a fossilized ripple from creation's first breath, a relic so primeval it makes black holes look like newborns. Whether they're theoretical ghosts or real cosmic architects, strings challenge our deepest ideas about spacetime, reminding us that the universe's boldest designs are often written in the thinnest of lines. From the hearts of distant galaxies, beams of pure energy erupt with such violence they pierce through intergalactic space, blazing across millions of light years like cosmic blowtorches. These are quasar jets, nature's ultimate particle accelerators, channeling the fury of supermassive black holes into narrow beams moving at 99.99% the speed of light. The Chandra X-ray Observatory has captured their brilliance, streamers of high-energy plasma stretching tens of thousands of light-years, glowing not with starlight but with synchrotron radiation, the telltale signature of electrons spiraling through magnetic fields at nearly light speed. At the source of these jets lies a monster, a black hole weighing billions of suns, gorging on gas and stars, but not all that falls inward stays trapped. Magnetic fields near the event horizon act like cosmic railguns, funneling some infalling matter into tightly collimated jets along the black hole's spin axis. The physics is staggering. Particles in these jets experience accelerations millions of times more powerful than anything in human-made colliders, reaching energies that make the Large Hadron Collider look like a child's toy. When these relativistic electrons encounter magnetic fields, they emit synchrotron light across the spectrum, from radio waves to gamma rays, painting the jets in surreal hues invisible to human eyes but blazing in Chandra's X-ray vision. One of the most famous examples, Quasar 3C273, boasts a jet stretching 1.5 million light-years, 15 times the diameter of our Milky Way. Its X-ray emissions reveal knots and shockwaves where the jet plows into intergalactic gas, creating sonic booms in the thin medium between galaxies. These collisions generate enough heat to vaporize planets instantly, yet they also seed galaxy clusters with heavy elements and turbulent energy, shaping the evolution of entire cosmic neighborhoods. What makes quasar jets truly humbling is their raw power. The jet from Galaxy M87, imaged by the Event Horizon Telescope team, pumps out energy equivalent to 10 billion suns, its particles dancing along magnetic field lines like beads on an invisible wire. Some theories suggest these jets could be the universe's dominant source of ultra-high-energy cosmic rays particles striking Earth's atmosphere with the force of a well-thrown baseball, all launched from black holes billions of years ago. Yet for all their destructive potential, quasar jets might also be cosmic gardeners. By heating gas in galaxy clusters, they prevent runaway star formation that would otherwise drain galaxies of their star-forming fuel too quickly. They churn and redistribute matter, ensuring a slower, steadier rhythm of stellar birth and death. In the grand tapestry of the universe, these relativistic beams aren't just destroyers, they're sculptors, shaping the large-scale structure of everything we see. Tidal forces are nature's ultimate tug-of-war, the invisible hand that can stretch a star into strands of glowing spaghetti or lift entire oceans with rhythmic precision. Near a black hole, these forces reach nightmarish extremes. Picture an astronaut drifting feet first toward the event horizon. Gravity's pull on their toes grows exponentially stronger than on their head, stretching their body like taffy in a process gruesomely dubbed spaghettification. The difference in gravitational acceleration just a few thousand miles apart becomes so severe that molecular bonds snap, transforming solid matter into a stream of plasma before vanishing into the abyss. NASA simulations reveal this horror in eerie detail. A star straying too close to a supermassive black hole doesn't just get swallowed whole. It's shredded into a brilliant arc of debris, heating to millions of degrees as it spirals inward. Earth experiences tidal forces on a gentler scale, yet they're no less profound. The Moon's gravity pulls our oceans into bulges, creating high tides on opposite sides of the planet simultaneously. But here's the twist: the Sun's tidal influence is actually stronger than the Moon's. Its immense mass should dominate, yet the Moon's proximity makes its tidal pull more than twice as effective. That's because tidal forces don't just depend on gravity's strength. They hinge on how quickly gravity weakens with distance, a principle called the tidal gradient. The Moon, being closer, exerts a steeper gradient, stretching Earth's oceans and even its crust with remarkable efficiency. Celestial bodies aren't immune to these cosmic stresses. The Roche limit, the minimum distance a moon or planet can orbit before tidal forces rip it apart, dictates the fates of countless worlds. Saturn's rings likely formed when a moon or comet ventured inside this limit, shattered by the planet's gravity. In 2018, astronomers witnessed a star crossing the Roche limit of a black hole 375 million light-years away. The result: a tidal disruption event bright enough to outshine its host galaxy for months, a flare captured by telescopes from ultraviolet to radio wavelengths. Simulations of these events reveal chaotic beauty. Gas from the disrupted star doesn't fall straight in. It forms whirlpools of superheated plasma that collide and spark X-ray outbursts detectable across the universe. Some particles get flung away at near light speed, while others spiral for years before meeting their doom. Even our own solar system bears tidal scars. Jupiter's moon Io, squeezed relentlessly by the gas giant's gravity, erupts with volcanoes as its interior kneads like dough. Tidal forces don't just destroy, they mold, shape, and sometimes even ignite the very processes that make cosmic landscapes dynamic. Whether stretching stars into luminous streamers or coaxing waves onto a beach, they're proof that gravity's gentle whisper can become, given the right conditions, the universe's most creative wrecking ball. Sunlight seems gentle from Earth's surface, warm, golden, life-giving, but our star has a violent side. Solar flares erupt from the sun's roiling surface with the force of 1 billion hydrogen bombs, hurling superheated plasma across the solar system at millions of miles per hour. These coronal mass ejections, or CME, are cosmic hurricanes of charged particles, capable of frying satellites, crippling power grids, and turning the night sky into a swirling aurora visible at the equator. The Carrington event of 1859 offers a chilling preview of what these solar storms can do. When a massive CME struck Earth's magnetic field, telegraph systems, the Victorian internet, sparked and caught fire worldwide. Operators received shocks through their equipment, and auroras lit up skies as far south as Cuba. Today, a storm of that magnitude would wreak unprecedented havoc. Modern simulations suggest it could knock out GPS satellites for weeks, disable undersea internet cables, and trigger continent-wide blackouts by overloading transformers with geomagnetic currents. The economic impact estimates top $2 trillion in the first year alone. Space weather monitoring has become our early warning system. NASA's Solar Dynamics Observatory and the European Space Agency's Solar Orbiter track sunspot activity in real time, while NOAA Discover satellite acts as a solar storm buoy measuring incoming CMEs. When a flare erupts, we typically have between 18 to 48 hours to prepare, enough time for airlines to reroute polar flights, satellite operators to enter safe mode, and power companies to brace for induced currents in transmission lines. Yet some flares defy prediction. In 2012, a Carrington-class ejection missed Earth by just 9 days, a near miss revealed years later by stereo spacecraft data. The Sun's surface simmers with activity in 11-year cycles, and we're currently entering solar cycle 25's peak. Even routine flares can dazzle. In 2017, a moderate CME triggered auroras so bright they confused migratory birds into singing at midnight. The true nightmare scenario, a solar superstorm like those detected in ancient tree rings and ice cores, events 10 times stronger than Carrington. These occur roughly once every 5,000 years and could plunge civilization into a technological dark age. That's why scientists are racing to develop better shielding for satellites, more resilient power grids, and advanced forecasting models. The next great flare isn't a matter of if, but when, and when it comes, we'll be staring directly into the sun's fury, hoping our preparations hold against the cosmos' most unpredictable storm. 4 billion years from now, an event of incomprehensible scale will unfold. The Milky Way and Andromeda, two spiral giants each containing hundreds of billions of stars, will begin a gravitational dance that ends in cosmic consummation. This isn't destruction, it's transformation. Simulations from NASA's Hubble team reveal a mesmerizing sequence. As the galaxies first approach, Their mutual gravity stretches tidal tails of stars hundreds of thousands of light years into the void filaments of light arcing through intergalactic space like celestial brushstrokes. Then, over billions of years, multiple close passes will shred their elegant spirals, mixing stars into a turbulent soup before settling into a single, football-shaped elliptical galaxy astronomers dub Milkdromda. Dark matter, the invisible scaffolding of galaxies, governs this collision with unseen hands. Though the galaxy's visible stars appear dense, they're mere fireflies flickering within vast halos of dark matter extending 10 times farther. As the halos interpenetrate, their gravitational drag slows the galaxy's motion, ensuring they don't just swing past each other but eventually merge. Stars themselves won't collide, space is too vast, but the interstellar gas clouds will, compressing into fiery nurseries where new stars ignite at rates dwarfing anything in today's cosmos. Supercomputer visualizations show these bursts of starbirth as blue-white fireworks erupting across the merging galaxies, their brilliance fueled by shockwaves from colliding nebulae. The aftermath resembles a celestial phoenix. Within 7 billion years, Milkdromda's core will blaze with the light of aging stars, their golden hues dominating the newborn galaxy's center. Our solar system, if it survives, will likely be flung outward into the galactic halo, orbiting this new leviathan in an eccentric path. But the true spectacle lies beyond. The merger will trigger a chain reaction, destabilizing nearby dwarf galaxies like the Magellanic Clouds, some of which may plunge into Milkdromda's maw while others escape entirely, forever changed by the encounter. What makes galactic collisions humbling is their paradox. Chaos on stellar scales births order on cosmic ones. The same forces that fling stars into the abyss also seed future generations, ensuring the universe never stagnates. And though the collision plays out over epochs far exceeding human imagination, its blueprint is already written in the gravitational codes of dark matter, the relentless pull that sculpts not just galaxies but destiny itself. In the vast cosmic laboratory, few events serve dual purposes as brilliantly as white dwarf supernova cataclysms, so precisely predictable they became the universe's yardsticks. These type Ia explosions begin with a stellar corpse, a white dwarf, the dense leftover core of a sun-like star. Normally, these Earth-sized embers slowly fade into darkness, but when a white dwarf steals matter from a companion star, it crosses a deadly threshold. Upon reaching 1.4 times the Sun's mass, a limit called the Chandrasekhar limit, its carbon core ignites in a runaway thermonuclear chain reaction, detonating with such uniformity that each explosion shines with nearly identical brightness. This consistency makes them cosmic beacons, allowing astronomers to measure distances across the universe with extraordinary precision. The brilliance of these standard candles revealed one of cosmology's greatest shocks. By comparing the apparent brightness of distant type Ia supernova to their known intrinsic brightness, scientists in the late 1990s made an unsettling discovery. The universe's expansion isn't slowing down as expected, it's accelerating. This revelation, which earned the Nobel Prize in 2011, pointed directly to dark energy's existence. Imagine tossing a ball into the air only to watch it speed away faster instead of falling back. That's the counterintuitive reality these dying stars exposed. Without their predictable light, we might never have grasped the cosmos's accelerating fate. Beyond their role as cosmic measuring tapes, these explosions are elemental alchemists. The inferno inside a type Ia supernova fuses carbon and oxygen into heavier elements like iron, nickel, and even gold, scattering them into interstellar space at thousands of miles per second. Nearly half the iron in your blood, the calcium in your bones, and the zinc fueling your immune system were forged in such blasts billions of years ago. When astronomers analyze the light spectra of these supernova, they see fingerprints of these freshly minted elements, direct evidence of how the universe recycles stellar ashes into new generations of planets and life. The aftermath of a Type Ia supernova is hauntingly clean. Unlike the messy remnants left by collapsing massive stars, these explosions leave no neutron star or black hole behind, just an expanding shell of glowing debris drifting through space. In 2015, the Hubble Space Telescope captured one such remnant, SNR 0519-69.0, in the Large Magellanic Cloud, its delicate filaments still radiating X-rays decades after the blast. These ghostly remnants serve as time capsules, preserving the conditions of the explosion for millennia. Yet mysteries remain. Recent observations of unusually bright or dim Type Ia supernova suggest there might be multiple pathways to destruction, perhaps involving collisions between two white dwarfs. Each outlier forces scientists to refine their models, ensuring these cosmic candles burn even more accurately as guides to the universe's darkest secrets. From measuring the cosmos's expansion to seeding it with the ingredients for life, white dwarf supernovae are proof that even in death, stars light our way forward. Some of the universe's most precise timekeepers aren't human, made their city-sized stellar corpses spinning faster than kitchen blenders, sweeping beams of radiation across space with metronome-like regularity. Pulsars, the rapidly rotating cores left behind after supernova, are nature's lighthouse beacons, flashing with such consistency they rival atomic clocks. Their secret lies in extreme physics. A neutron star's intense magnetic field, trillions of times stronger than Earth's, funnels radiation into narrow jets along its magnetic poles. As the star spins, up to 700 times per second for the fastest known, these beams sweep past Earth like a cosmic strobe light, producing pulses detectable across interstellar distances. The discovery of pulsars in 1967 by Jocelyn Bell Burnell initially baffled astronomers, who jokingly labeled the signals LGM for little green men. But these weren't alien transmissions, they were the unmistakable fingerprints of neutron stars, objects so dense a teaspoon of their material would weigh 1 billion tons on Earth. What makes pulsars revolutionary is their precision. The Crab pulsar, born in a supernova observed in 1054 AD, flashes 30 times per second with a regularity that drifts by just 1/10,000th of a second per year. This stability allows scientists to conduct extraordinary cosmic experiments. Einstein's theory of general relativity gets its most rigorous tests from pulsar observations. When astronomers discovered the first binary pulsar in 1974, they noticed its pulses arrived slightly earlier or later depending on its orbit, proof that the system was losing energy through gravitational waves exactly as Einstein predicted. This earned the Nobel Prize in 1993, decades before LIGO directly detected such waves. Even more extreme is the double pulsar system J0737-3039, where two neutron stars orbit each other every 2.4 hours, warping spacetime so severely that their pulses serve as precision probes of relativistic effects like geodetic precession and Shapiro delay. But pulsars have another trick, they're planet hunters. In 1992, minute variations in the pulse timings of PSRB 1257+12 revealed the first confirmed exoplanets, dubbed Draugr, Poltergeist, and Phobder. These weren't cozy worlds, they orbited a stellar graveyard, bombarded by lethal radiation, but their discovery proved pulsar timing could detect planetary bodies smaller than Earth. Modern techniques can now spot shifts as slight as 100 nanoseconds, sensitive enough to find moons around alien pulsars if they exist. Some researchers even propose using pulsar networks as galactic GPS systems, their predictable flashes serving as navigation beacons for future interstellar travel. What makes these cosmic lighthouses truly humbling is their duality born from stellar violence. They've become tools of exquisite precision. From verifying spacetime's curvature to uncovering hidden planets, pulsars remind us that sometimes the universe's most useful instruments aren't built in labs, they're forged in supernova. Deep in the cosmos, invisible bullets streak through space at nearly light-speed cosmic rays, atomic fragments carrying energies so extreme they challenge everything we know about physics. These aren't just stray particles, they're protons and atomic nuclei accelerated to unfathomable velocities, some packing the kinetic energy of a major league fastball, all concentrated into a single subatomic speck. The most energetic cosmic ray ever detected, nicknamed the "Oh my God" particle, hit Earth's atmosphere in 1991 with roughly 50 joules of energy equivalent to a falling brick, but compressed into a particle smaller than an atom. If you held out your hand, one of these ultra-high-energy cosmic rays passes through your palm every few seconds, most harmlessly, but the rarest, most powerful ones. They carry mysteries that have baffled scientists for over a century. These cosmic bullets don't announce themselves directly. Instead, they trigger sprawling air showers when they collide with atmospheric molecules. Picture a single high-energy proton slamming into an air nucleus 50 miles overhead. The impact spawns a cascade of secondary particles, pions, muons, electrons multiplying exponentially until billions of fragments rain down over several square miles. Giant detector arrays like the Pierre Auger Observatory in Argentina catch these sprawling particle downpours using tanks of ultra-pure water. When secondary particles zip through the water at relativistic speeds, they emit faint blue flashes of Cherenkov radiation, ghostly fingerprints of the original cosmic ray's identity and energy. The puzzle: we still don't know what cosmic accelerator launches these particles with such violence. Even the most powerful known astrophysical engines, supernova, neutron star mergers, fall short by orders of magnitude. The leading suspects lurk in the hearts of active galaxies, where supermassive black holes like Messier 87's beast spew jets of plasma stretching thousands of light-years. These relativistic jets might act as natural particle colliders, boosting protons to energies 100 million times beyond what the Large Hadron Collider achieves. Yet some cosmic rays arrive from seemingly empty voids, regions devoid of obvious power sources, hinting at entirely unknown phenomena, perhaps cosmic strings or decaying dark matter. What makes cosmic rays more than just a physics curiosity is their role as interstellar messengers. By analyzing their composition, especially the ratio of heavier nuclei like lithium, beryllium, and boron, scientists reconstruct their interstellar journeys. These elements are cosmic ray spallation products, forged when high-energy protons smash into carbon and oxygen atoms drifting between stars. The longer a cosmic ray travels, the more of these secondary elements it accumulates, turning each particle into a clock recording its own history. Some bear traces of radioactive isotopes like iron-60, suggesting they recently passed through a nearby supernova's debris field, stellar shrapnel still lingering in our galactic neighborhood. For all their destructive potential, cosmic rays also play a quiet role in Earth's story. When these particles strike nitrogen molecules in the upper atmosphere, they generate carbon-14, the isotope that revolutionized archaeology by enabling radiocarbon dating. More eerily, some researchers speculate that cosmic rays might influence cloud formation by ionizing atmospheric molecules, potentially nudging Earth's climate over millennia. And let's not forget biological impacts. Astronauts on the Moon or Mars, beyond Earth's protective magnetic field, face a constant drizzle of these high-energy particles, each capable of damaging DNA. Future spacefarers might need shielding lined with hydrogen-rich materials like polyethylene, ironically, the same stuff in grocery bags, to scatter incoming cosmic rays before they pierce human tissue. The next generation of detectors promises to peel back more layers of this cosmic mystery. The Cherenkov telescope array, under construction in Chile and the Canary Islands, will hunt for gamma rays emitted alongside ultra-high-energy cosmic rays, tracing them back to their sources. Meanwhile, space-based experiments like the planned JM USO telescope on the International Space Station will scan the atmosphere for the faint ultraviolet glow of air showers from orbit. Every new detection is a breadcrumb leading us closer to understanding the universe's most powerful particle accelerators, engines hidden in plain sight, hurling fragments of atoms across the cosmos with forces we're only beginning to comprehend. Einstein's equations hold a secret buried in their math, a hidden shortcut through the fabric of spacetime itself. Wormholes or Einstein-Rosen bridges aren't just science fiction. They're valid solutions to general relativity, tunnels connecting distant points in the universe like cosmic subway lines. Picture folding a piece of paper so two dots touch. The wormhole is the pen stroke piercing through, turning a billion light-year journey into a stroll across the void. But before you imagine hopping through one, there's a catch. These theoretical passages would snap shut faster than you could say, black hole, crushed by their own instability unless propped open by something truly exotic. Science fiction loves to depict wormholes as stable, traversable highways. Think Interstellar's Gargantua or Stargate's shimmering portals. Reality is far less forgiving. General relativity permits wormholes, but they'd require exotic matter with negative energy density to keep their throats open, a substance that defies known physics by exerting anti-gravitational pressure. The closest real-world analogues might be quantum phenomena like the Casimir effect, where closely spaced plates in a vacuum experience a slight negative energy. But scaling this up to stabilize a wormhole would demand energies beyond anything we can currently conceive. Recent breakthroughs in quantum gravity hint at wilder possibilities. Holographic principle theories suggest wormholes might be entangled quantum states in disguise, their interiors encoded on distant event horizons like a cosmic version of quantum teleportation. Simulations using entangled black holes, dubbed ER=EPR, after landmark papers show particles connected through wormholes could behave as if information teleported between them. It's as if the universe glitches, linking 2 points not through space but beneath it. Yet the most tantalizing twist involves time. A wormhole with one end accelerated to near light speed could, in theory, become a time machine. The twin paradox, where a traveling astronaut ages slower than their Earth-bound sibling, would apply to the wormhole's mouths, creating a bridge not just between places but between epochs. Step in one side, exit the other a century in the past. But here's the rub. Quantum mechanics abhors time loops, with laws like Hawking's chronology protection conjecture acting as cosmic circuit breakers to prevent paradoxes. Astronomers aren't just theorizing, they're hunting. Some propose certain gamma-ray bursts or strangely lensed quasars could betray a wormhole's presence. Others suggest the mysterious cold spot in the cosmic microwave background might be a bruise from a neighboring universe's wormhole brushing against ours. While proof remains elusive, the math keeps revealing a universe far stranger and more connected than we ever imagined. Wormholes might not be the interstellar subway system of our dreams, but they're proof that spacetime is anything but rigid. It's a dynamic, twistable fabric full of secrets waiting to be pulled taut. From the quiet persistence of gravity to the explosive fury of supernova, the 30 titans we've explored form a cosmic hierarchy of power, each shaping the universe in ways both violent and delicate. Gravity lays the foundation, bending spacetime into galaxies and planets, while electromagnetism paints the cosmos with light and binds atoms into the chemistry of life. The strong nuclear force locks quarks into protons, forging the elements in stellar furnaces, while the weak force quietly transmutes elements, ensuring stars burn and planets form. Dark matter weaves invisible scaffolds for galaxies, and dark energy stretches the void between them, their unseen rivalry dictating the fate of all things. Black holes devour stars, neutron stars collide to forge gold, and gamma-ray bursts scream across the cosmos, etching their violence into space itself. Yet the most humbling realization isn't the scale of these forces, it's how intimately they shape us. The iron in your blood, the calcium in your bones, even the electricity firing through your neurons, all were forged in the hearts of dying stars, scattered across the universe by forces beyond comprehension. We are stardust made conscious, fleeting witnesses to a cosmos seething with powers that could erase us in an instant. And yet, here we are, small, fragile, but curious enough to unravel these mysteries. The universe doesn't care about our existence, but that's what makes our quest to understand it so extraordinary. From unraveling quantum entanglement to hunting for wormholes, each discovery peels back another layer of reality, revealing a cosmos stranger than fiction. So the next time you look up at the night sky, remember, those distant lights aren't just stars. They're the fingerprints of the forces that built everything, including you. If these cosmic titans left you awestruck, smash that like button and subscribe, because the universe still holds countless secrets, and we're just getting started. The cosmos is vast, violent, and utterly magnificent, and together we'll keep uncovering its wonders, one mind-blowing revelation at a time.